3 of a series that I'm making about inflation and the Consumer Price Index, also called the CPI for short. In previous videos, we looked at the United States CPI, Consumer Price Index, for 1975 and 2005, and used it as a way to try to understand or mathematically model inflation to make estimates for prices and salaries. For example, if a gallon of gas was 50 cents per gallon in 1975, we took the ratio of 195.3 divided by 53.8, which ends up being about 3.6, and multiplied it by 50 cents to get an estimate of $1.82 per gallon of gas in 2005. We can also go backwards and say if a gallon of milk in 2005 was $2.75, we take the ratio of this thing divided by this thing, which is about 0.26 or 0.27 or so, and multiply that by 275 to get this 76-cent estimate for the price of a gallon of milk in 1975. Now again, I'm not taking official numbers here, except for the CPIs as far as these prices go. I'm just making estimates. I should give you a word of warning that I didn't really emphasize in the previous videos. Just because, say the price of a gallon of gas was $1.80 or so in 2005, does not mean that a gallon of gas is less affordable in 2005 than it was in 1975, even though the price is higher. Because, generally speaking, salaries are going up as well. What the CPI is really saying is, if the price in 2005 was about $1.80, compared to a price of 50 cents a gallon in 1975, that those prices are actually equivalent in terms of their affordability, generally speaking, because they're matching the rate of inflation. Now, I believe gas was more than this. It was maybe $2 to $2.50 or so in 2005. And if that's true, that actually means gas was less affordable in 2005 if it was 50 cents in 1975, because $2 is more than the estimated $1.82 that would come from the CPIs, as well as this estimate. But if it had been $1.80, they would have been basically equivalent. We also looked at different salaries in different years that would be equivalent in terms of their buying power. They're giving you the same kind of standard of living in the same kind of way using the CPIs. We also made this big chart where we looked at historical data for the CPIs from 1973 up until 2012. I'm making this video in 2013. And we see that the change in the CPI helps you figure out the relative change in the CPI, and this is an annual rate, to estimate the inflation for that given year. So this 11% that you see here is the estimate for inflation from 1973 to 1974. It was a relatively large change in the CPI between those 2 years, meaning prices are going up pretty fast. The biggest one was this one, 1980 to 1981, biggest relative change, and then after that point it gets considerably smaller over the years, and there was even a year where it was negative because of the recession in 2008 into 2009. All right, in this video, what I want to do is I want to try to model inflation, in particular model how the CPI changes over time. See if we can figure out a good function, and we'll keep it basic, we'll make it an exponential function that will show how the CPI goes up over time. Now, long term, that won't work real well because inflation was so high in the 70s and early 80s and then so low afterwards. But let's look at a fairly short time period here from 1973 to 1983, say, and see if we can't model the CPI as a function of time over those years. So let's type out a plausible equation for this function. CPI is going to be a function of time, so the dependent variable I probably should call CPI. That's supposed to represent one quantity, the CPI. And hopefully you recall with exponential functions you want to take the initial value of the dependent variable, which often you still call the same name as the dependent variable, CPI in this case, but then put a subscript of 0 to emphasize that it's an initial value. And that's not a variable, that's going to be a constant for us. We want to multiply that constant by some quantity, probably slightly bigger than 1, raised to the t power, let's say, where t is time in years, since 1973. I'm going to call that quantity 1 plus r to emphasize that it's slightly bigger than 1. And in fact, r will be the overall average inflation rate, you might say, during the time period that we're looking at. So here's our equation showing us our model for the situation. Again, CPI is the dependent variable. It's a function of t, time in years, since 1973. Time equals 0 is going to correspond to 1973. CPI sub 0, this quantity, this entire thing represents the initial CPI in 1973. That was 44.4, I believe. And then R is going to be the inflation rate over the number of years that we are using this function for. It's an overall average inflation rate. We're going to do it over a 10-year period here. And in fact, we're just going to use the data at the beginning year, the 44.4, and the ending year, 10 years later, in 1983, had a CPI of 99.6. We're just going to use that data. We're not going to use the data in between, even though it would be relevant to do so and probably give us a more accurate model in the long run if we did so. Let's see, I lost my formula here. Okay. So I'm going to use that data. How? Well, I'm going to plug in 99.6 for the CPI in 1983, which is 10 years after the CPI in 1973, 73 being year 0. 44.4 was the initial CPI in year 0 in 1973, so I want to plug that in there. And this is the equation that I need to now solve for R to help me come up with my model. So I'll put that in there. How would you solve this equation? You want to isolate R. I'm going to go through this pretty quickly. You might want to try to write these steps down on your own, but I'm going to go through them pretty quickly. You want to divide by 44.4 first, so that it divides out on the right side there and leaves you with a 1, leaving you ultimately with a 1 plus r to the 10th power on the right side of the equation. If I do it to the right side, I also have to do it to the left side. 99.6 divided by 44.4 is about 2.24324. Technically speaking, that's more significant digits than I should use. However, I'm going to use all those decimals in this situation because I only want to round at the end. If you round too soon, then the errors kind of compile on each other, and your estimate at the end could be less accurate. So I'm going to keep all those digits of accuracy. What do I need to do? That number is being equal to 1 plus r to the 10th power. I need to then get rid of that 10th power by raising both sides to the 1/10th power. So here's where I'm going kind of fast. So I'm going to raise this thing to the 1/10th power, 0.1 power, and that'll equal 1 plus r. Maybe stop, think about that. Are you back? Did you write it down? Really, we had 2.24324 equal to 1 plus r in parentheses to the 10th power. I want to get rid of that 10th power by raising both sides to the 1/10th power. If I do it to the right, I have to do it to the left, so I have to take 2.24324 and raise it to the 1/10th power and get this, and that's going to equal 1 plus r. So r, now I can find by subtracting 1 from this, r is going to be this number minus 1, though now I really should round. This is too many significant digits. In my model, I'll use an r of, let's say, 0.0841. So r is 0.0841. How does the model do? Let's now test it against reality. We will use it. I'll call this a CPI estimate. I know I went over the r there. Let's put the r up here. So I'm using the formula. First of all, I've got a 44.4 times 1 plus r. R is in cell F12. to the t power. What's t? T is years since 1973. I could type that in like that. That's going to give you the number of years since 1973. When the year is 1973, it's going to be a 0, the power there. When the year is 1974, you're going to get a power of 1. When the year is 1975, you're going to get a power of 2. When the year is 1983, at the end, you're going to get a power of 10. And it matches up the initial value, and the ending value should match up pretty close. We should get close to 99.6 here. A little bit off maybe because of rounding. Oops, something's wrong there. Let's see, what did I do? Oh, I need dollar signs, yeah. You teachers make mistakes too. I need dollar signs to keep that cell reference fixed. And now copy and paste this down. Sorry, can't see it here. There we go. It does match up pretty well there in the last year. What about these other years? How well does it match up? Well, instead of trying to compare them one by one, let's make a quick graph of all of this and see how the graphs compare. So I'll go up to charts here, make a scatter plot to connect the dots. I believe that, yeah, the blue is the actual CPI and the red is our exponential model. You can see, generally speaking, it's too low, though in these middle years it's a little bit too high. Overall, it's not too bad, and I'll end this video with that graph.